What are we going to do with this guy? Let's click those close there. What do I always try to do first? Plug it in. Okay? So if I plug this in, what happens? What do I get here? Which is 0 over some number, right? So what's the answer? 0, right? And do I really need to know on this one? Do I need to put like 0 plus? No, it doesn't matter, right? Doesn't make any difference. If I evaluate this and I get 0 divided by some number, the answer is 0 and I'm done. That's the limit. It worked. Okay, the point is, don't just, I mean, I know, and it would make sense. I mean, like we do calculus in discrete little steps where we practice skills, and typically, on the assignment, you're going to be practicing a handful of skills, and so you kind of get in the habit of just assuming the problems are going to be practicing that skill, where you're taking infinite limits. But don't lose sight of the fact that we always want to just try to evaluate directly first and see what happens, because sometimes we're off the hook. We just get an answer and we don't have to do anything, right? Like in this case. Okay, what about this one? Just quick review. That is one where I'd get 0 over 0, isn't it? Right? Okay, so what are we going to do? Okay, factor 3 out of the top. Good. So, and I'll just pull that 3 out in front of the limit even. Okay, we're still getting 0 over 0, so what else do we need to do here? Darn it. There we go. There you go. Good. Factor the top. And right, we get cancellation. And so now the indeterminacy is going away. Now what? Plug it in. Does this part, this plus, is that really important here? No, I mean, we're approaching 5 from the positive side, but it doesn't matter which side we approach 5 from. We're getting the same answer either way, aren't we? We're just getting, we're getting an answer that is not indeterminate, where we have just a number. 3 times, this is going to become a 5, so this whole factor becomes 10, right? So 3 times 10 equals 30, and we're done. Okay? Thumbs up, down, sideways, how we doing? Okay? Good? Okay. How about these? Okay, we got problems there, don't we? A little bit. I mean, we end up with 0 on the bottom, right? Get a number over 0 on that top one. So what's that tell us? Number over 0. If we go back to the our kind of closer to the beginning of the year when we talked about limits, we get 3 types. This was a good one, right? We got an answer. We're done. If we get 0 over 0, we have to do more work, right? Have we had one of those yet? Well, this was originally 0 over 0, right? So we had to do more work. Or we get one like this, where if I try to evaluate it, I get some number divided by 0. Used to be D&E, does not exist. But now we're going to be more specific about that. If we're approaching 4 from the right, what additionally could you say about that? On the top, we're getting what? 16, negative 2, is that right? Okay. On the bottom, what do we get? Four plus minus 4 is what? 0 plus, right? Small positive number squared. 0 plus squared is what? 0 plus, agreed? Small positive number squared. is a small positive number. Well, we got a 0 on the bottom, so we know we're getting an infinity. What's the sign going to be? Negative, because I've got a negative number divided by a positive number. Okay? What's the answer going to be? We could do this one right away. What's the answer going to be? Same, right? How come? Because we know we're getting the same thing on the top. What are we getting on the bottom? 0 plus, aren't we? Because it's being squared. No matter what flavor of 0 that is, when we square it, it's becoming a 0 plus, isn't it, right? So we get a negative infinity. So what's the answer to the two-sided limit then? Negative infinity, right? Because these two both agree, we can say negative infinity. Now, if one of these had been negative and one had been positive, then we would have just had to have said doesn't exist. The two-sided limit doesn't exist because they didn't agree. It still doesn't exist, but at least now we know it consistently doesn't exist in the positive infinite direction, right? Okay? All right, so this is kind of this one doesn't come up in textbooks, but it's something that I want you to know about because you'll see this eventually in college. It's kind of a little bit of a strange one, but this is something that is pervasively done incorrectly in calculus. It's just, and you'll see that sometimes. Sometimes people make the statement that 0 divided by 0 is always a whole, right? And we may have even said that back in Algebra 2. At the time, that's all we were going to see was 0 over 0 is a whole and a number over 0 is a vertical asymptote, right? But it turns out that 0 over 0 is still indeterminate. It might end up being a whole, usually it probably does, but it could still end up being a vertical asymptote after you remove the indeterminacy. So really the way the rule should go on this is, after removing the indeterminacy, if direct substitution yields a limit of the form a over b, where b is not equal to 0, then the function has a whole, right? Like, for example, we did a problem like this just a little bit ago, right there. Right? Initially, we had an indeterminate form. If we tried to evaluate that directly, we got 0 over 0, right? We canceled the offending factors, right? The factors that were causing the indeterminacy, and we got an actual answer. So what's that saying? Well, this filled in the hole, didn't it? When we canceled those factors, fill in, or actually I think a word that they use in the AP videos, don't they say plug the hole? And I think they do, don't they? I think they do. Pretty sure they do. So we're plugging the hole when we cancel those factors, and this is the value where the hole exists, right? If we want to fill the hole, we would just give the function this value at 5. Okay, give me thumbs. Does that make sense? Okay, but that doesn't always happen, right? So if you can remove the indeterminacy and get an answer, then that was a removable discontinuity, and you just plug the hole, right? But after removing the indeterminacy, if the direct substitution gives us a number divided by 0, well, then it turns out that it wasn't a hole. It was actually a vertical asymptote. Okay, let's look at an example like that. Like, what about this guy here? If I try to evaluate this directly, what do I get? Oh, sorry, I guess we're not taking a limit, are we? Let's take the limit of this. As x approaches 2. What do we get there? 0 over 0, right? So that's indeterminate, right? Okay. But it's not necessarily a whole. Probably is, could be, but it's not necessarily. We've got to remove the indeterminacy and see what it is. Well, we know how to remove indeterminacy. In this case, we got to factor it and cancel factors. So what's that? X minus 2 times x minus 2, right? X minus 2 squared. Let's just write it that way. Cancel like factors, right? So we can do this. Right? And so we end up with the limit of, oh, this one worked out, didn't it? Yeah, this one worked out. Okay, that one worked. So that was a whole, right? Did I have this built for one of those? Maybe I didn't. I guess I just got to make it up on the spot here. That's all right. So, what? Oh, sorry, 0. Yep, you're right, 0. Okay, but 0 works, right? 0 is an answer. Okay. We get it. So that was a whole, right? The value of the function is 0. Okay, but what if we had this function instead? Just the reciprocal of the past one, right? So everything factors the same. So again, we cancel the x minus 2's, and if we evaluate it this time, we get 1 over 0, right? So this one actually does end up having a vertical asymptote. Make sense? And now we could be more specific if we were taking a one-sided limit here. What if we were approaching 2 from the right? Well, then we would have ended up on the bottom having 2 plus minus 2 is 0 plus, right? So we just would have had positive infinity. Everybody agree? Okay. Now, do you get, I don't know if I was clear enough on that. You get my point, though. The point is, when you start off with an indeterminate answer, you know, in first-year calculus, I mean, probably every time in every textbook, first-year calculus textbook, you're going to end up getting a hole there. But my point is just that you don't actually have to, right? You can't just assume that. You first have to resolve the indeterminacy and see what happens. If you actually get a number for your limit, yeah, then it's a hole. But when you resolve the indeterminacy, even though I started off with 0 over 0, I ended up with an asymptote. It can happen, right? You actually have to do that work before you can just make the assumption that it's a hole. Okay? Thumbs. Okay, good. Minor little issue, but it's something that I remember it happened to me in college, so I don't want it to happen to you. I didn't know that going into college. Suppose, okay, how about this one? Let's look at a little application of this. So, this is kind of fun stuff. Suppose, have you guys talked about relativity in physics yet at all? Not really. I'm not sure if you will or not. It's not, you don't always talk about it in high school physics. It's classical physics. But some strange things happen when you approach the speed of light. And these are actual, this isn't just hypothetical. This is very real. This stuff definitely happens. So if you approach the speed of light, your clock runs slowly, first of all. So anybody got a twin here? No twins? Twins. Let's just say that your brother, you and your brother are, one of you is going to go, you're going to go on a little mission. You're going to take a mission, and you're going to get on this spaceship. It's going to accelerate at 1g, and it's going to continue to accelerate all through nether regions of the Milky Way and come back. And a year later, you're going to be back home. It's going to accelerate and do a big loop and come back and then decelerate at the end. and you get off so you get going really fast, right, during your trip. Before you leave, your brother gives you a parting gift, which is a nice watch. Okay, very nice wristwatch. It's battery powered, it keeps excellent time, never fails. You faithfully mark your calendar the whole time you're there, and it's exactly 1 year anniversary when you get back to Earth after your journey through the Milky Way. You step off the rocket, and you're expecting a big party from your brother, and he shuffles out there with his cane and wants to go play bingo with you. That's his idea of the party, because he's aged 70 years and you've only aged a year, right? Is that science fact or science fiction? Well, that's science fact. That would really happen. That's called relativistic time dilation. Moving clocks do run slowly. It's if I were to drive by in a spaceship and hold up a big clock out here as I was driving by, and you guys did the same thing, right? You did the same thing. You held up a big clock. I would see my clock running normally, but you would see it running very, very slowly. You would see the seconds ticking very slowly as I'm driving by you at near the speed of light. Incidentally, I would see the same thing, because from my reference frame, you're going by me, and I'm at rest, right? But moving clocks run slowly, okay? Another thing that happens is mass increases. Okay, as you move faster, your relativistic mass increases. An object has rest mass, like this pen has. I could put it on a balance and figure out what the rest mass is, right? But if I were to accelerate this thing close to the speed of light, it would accumulate a whole bunch of mass, and as a consequence, if it ran into something, it would have all this extra energy, because of its mass and its velocity. But it has a tremendous amount of momentum then because of the mass it's picked up. That's why you could never take any object of any mass at all, like take something extremely small like an electron, vanishingly small mass, but even an electron you cannot push to the speed of light. Usually these big accelerators now, like CERN, they don't accelerate electrons anymore. They usually accelerate bigger particles, so they don't go quite as fast. But like at the Stanford Linear Accelerator, they accelerate just electrons. That was kind of their forte, was very light particles. So they would, I don't know if anybody ever seen the Stanford Linear Accelerator? It's about a 3.5 mile building, just straight building, up in the kind of the hills just west of campus. When they would pulse the klystrons and generate these huge fields and shoot these packets of electrons down into the containment ring and separate the positive and the negative positrons from the electrons and collide them, it would be simultaneous, or at that instantaneous, the time of the actual execution of the experiment, it'd be using more power than the rest of the Bay Area totally combined in just this little packet of electrons, all that energy. But still, they couldn't go the speed of light. They could go very close, 99.99% the speed of light, but they could never go the actual speed of light, right? They just get very, very close because of this relativistic mass increase. Okay, the third thing that happens is Lorentz contraction. So you get this length contraction. If I were driving by in a really souped up car that, let's say at rest it's 20 feet long, and I'm driving by not just really souped up, but I mean extremely souped up. So I'm going, say, 99% the speed of light. I'm going very, very fast. As I go by you, if you were watching, let's say you had a really high-speed camera and you were able to run it back and look at it in slow motion, what you would see is that the car would have been compressed along the direction of motion. So the profile of the car would have looked the same. It would have been just as wide and as tall as it normally was, but from front to back, it would have been massively compressed. Instead of being 20 feet long, it might have only been an inch long. And there might have been a moment where I was going through a really narrow tunnel that's only a couple inches wide, and you could have taken a picture where the car was completely hidden by that tunnel, and it would have been. That really happens. There really is this physical contraction of objects as they move close to the speed of light. Now, I don't notice it in the car. I think everything's normal. In fact, what I see is all you guys you get like cutouts. You get real skinny, and I can see your profile, but you just, you don't have any depth to you. Those things really happen. Okay, so long story short here, we're going to do a little calculation of this. So let's calculate this length contraction that we get when we're traveling close to the speed of light. If we're so this is the formula in physics for calculating relativistic length of an object. Okay? It's equal to its rest length times what we call the gamma factor, the square root of 1 minus v squared over c squared, where v is my speed, c is the speed of light. When are we out of here? We got a little time, don't we? Okay. C is the speed of light. What is the speed of light, by the way? Anybody know? $300 million meters per second, roughly. It's about 186,000 miles per second. So it's fast, right? Very, very fast. What if our ship is, or whatever we're in, you know, I guess the spaceship, is traveling at 50% of the speed of light? What's the observed length going to be? Well, we can just evaluate that, right? This is a function. We can just write this as L of v, because v is the variable. C is constant. That's the speed of light. The rest length is constant. We just measure that when it's at rest, and that doesn't change. So L of v is equal to L naught times the square root of 1 minus v squared, over c squared. So if I evaluate this at 0.5 c, half the speed of light, what do I get? Square root L naught times the square root of 1 minus 0.5 c quantity squared divided by c squared, right? Well, the quantity 0.5 c squared is just 0.25 times c squared, agree? Everybody buy that? Okay, so we get L naught times square root of 1 minus 0.25 c squared over c squared, and the c squareds cancel. So I just get L naught times the square root of 1 minus 0.25. Well, that's just the square root of 0.75. Okay? So let's put that in Desmos. I'm going to call this x instead of v. We're going to call x our velocity. And I'm going to call a my initial length. Okay? Okay, C, we're going to set C, that's 300 million, so 300, okay. I'm just going to let the length be 1 for a second, so we'll end up just getting a number here. So we're going to do 0.5 c. What's that telling me then? Oh, you can't see that, can you? Whoops. Okay, so again, you missed all that, but there's my function. A is the length, right? I'm just going to call it 1 for now, right? So we're just going to end up getting, you know, kind of the what fraction of the original length. If I say that equal to 1, that just goes away. We're just getting a decimal or a fraction out of this, right? So if I let, you know, C is 300 million. If I evaluate this at 0.5 C, what's that telling me? What percentage of the original length is the spaceship going to be? Yeah, roughly 86.7, you know, okay, or 86.6. So there's the percentage. So it shrunk a little bit. Okay? We could do the same thing here. What if it's traveling at 75% the speed of light? Well, it's just a simple calculation. Now instead of squaring 0.5, we're squaring 0.75 c, right? And if I plug that into Desmos, let's make that a 0.75 c. And now what's my length? What percentage of the original length is the spaceship? About 66, right? Okay, and we can continue this, right? What if we're going, okay, so in parts A and B, what happens to the length as the speed of the ship increases? Well, it's getting smaller, right? We already talked about that. It's getting smaller. Okay, but now let's figure out what's going to happen if we start to push this closer and closer to the speed of light. Let's see what the limit's going to be. You know, what's going to start to happen. So let's take a limit. Now, do you see, can anybody tell me why is this a one-sided limit? We're taking the limit of this function as v approaches c from the left. How come? Okay, it'd be taking the square root of a negative, which we can't do, right? Physically, what's going on? How come it's got to be from the left? Say it again. Okay, I'm moving in a positive direction. Okay, and we'll just call this even speed, so we don't worry about direction here. But why can my speed only approach c from the left, meaning from values less than c? I can't get bigger than c. Right? That's Einstein's law. Nothing with mass can ever go the speed of light. So we can approach it, but we can only approach it from values less than the speed of light. Like starting at 0, we would just be accelerating and accelerating and accelerating and pushing the limits closer and closer and closer to the speed of light. But what we're going to find is we could never actually get there, right? We just can't quite get there. And the reason we can't get there is because the mass increases so much that all the force we're using to accelerate us eventually gets eaten up by that extra mass. It's harder and harder and harder to push something, right? Okay, so we got to take this limit. Well, I mean, I can't really do that using Desmos anymore, right? Because I can't take a limit with Desmos. I mean, I could get really close. I could say 99% the speed of light, and then it's only 14% of the original length. Or I could do 99.9% the speed of the light, and then it's only about 4.5% of its original length. And I could keep doing that, but I'm just really just plugging in numbers. I'm not getting an actual answer to my limit. So this is where we got to use calculus, because we have to actually take this limit. So what happens then? We've got our function up here. So we want to find out what is the limit of L naught times the square root of 1 minus v squared over c squared as v approaches c from the left. Okay, well, we can evaluate this, right? This is a constant, agreed? Square root of 1 minus, if v is approaching c from the left, this is looking like c minus squared, agreed? Okay. Okay, what is c minus? And I could even write that. How about if we could even write that one more time. This should be a limit. Well, let's write it this way. We've evaluated the limit. I could factor out that squared, and that's just c minus over c quantity squared. What's c minus over c? Slightly less than what? Than 1, agreed? Okay, slightly less than 1. This is a number just a little less than c divided by c is going to give us a number just a little less than 1, right? So that's like saying 1 minus. Right? And 1 minus squared is just another number that's very, very close to 1, agreed? That's the same thing as 1 minus, right? Like 0.99999 squared is just 0.999. Something, I'm going to get something close to 1, but slightly less. So I get L naught times 1 minus 1 minus, right? What's 1 minus 1 minus? 0 plus, right? I'm subtracting something slightly less than 1 from 1, and I'm getting 0 plus, and the square root of 0 plus is 0 plus, right? Well, what's any constant times 0 plus? So what's the answer to this then? What's the limit of the length of an object as its speed approaches the speed of light? Yeah, 0, right? From the plus side, right? It's approaching 0. It's getting vanishingly small. Okay, that's kind of cool. I mean, we can actually do some stuff now. For the first time in your life, you can actually do some real math here. You can do some, I mean, this is like relativistic math. Okay. Okay, we don't, I don't think we'll, you tell me what would happen here without actually doing, just what's your intuition tell you? So if the relativistic mass now is equal to the rest mass divided by that gamma factor, right? If we do the same limit as V approaches C from the left, didn't we just get a 0 plus out of that whole thing? Right? So in the limit then, the limit of my relativistic mass as V approaches C from the left is just my rest mass divided by 0 plus. Well, isn't that just some constant divided by 0 plus, some positive constant divided by 0 plus is positive infinity, and there's why nothing can go the speed of light, because its mass approaches infinity.